we're going to talk about acid and base sensitive functional groups today because we're going to learn about how to protect those groups so that they don't react in a reaction. We're also going to think about oxidation or reduction sensitive functional groups. So as you might imagine, this is the chapter about ketones and aldehydes. And so those are certainly sensitive to oxidation if you're an aldehyde, to carboxylic acid. They're sensitive to reduction with hydride reagents and H2 reagents and things like that. So we're going to learn the way that chemists actually make molecules, and the fact that we really have to think through the different sensitivity to different functional groups. You know, we think of organic chemistry class as just organic chemistry, these molecules, trying to piece them together. But actually, we're just teaching you to be smarter. We're teaching you how to use logic, and this logic applies to many other classes. And so protecting group strategies is like a logical way of thinking about how to make complex molecules. So it's one of my very favorite lectures to teach because these are used quite often. All right, so the last mechanism that we learned, I'm going to review, and then we're going to get into some of those multi-step synthesis questions. This is where it gets kind of exciting because we need to think about what functional groups we have and what functional groups we need to make, and if they're sensitive along the way. So this is kind of the point in the class where it really hits of like how chemists rationalize and think about making molecules. So I don't know, it's one of my favorite lectures. All right, so we're going to review learning objective. Oh, less learning objective. We're going to review learning objective 18I. This is what we did at the end of class. It was that mechanism in which we were having two equivalents of an alcohol. Part of the reason I'm reviewing this is that it's a really key mechanism, and of course people had some issues with snow on Wednesday, so I'd just like to make sure we're all on the same page here. It's also going to be a mechanism that just comes up over and over again. So we're going to talk about the 4 P's of formation of acetals and ketals. Remember, acetals and ketals come from different functional groups. So they come from aldehydes, which is what an acetal comes from. And the ketal comes from a ketone. And we react these with alcohols. This is chapter 18.8 if you're following along in the book. All right, so what we learned on Wednesday is the fact that when we take an aldehyde or a ketone, we treat this as our electrophile. And then we need 2 equivalents of some sort of alcohol as our nucleophile. Remember, if you're struggling identifying electrophiles and nucleophiles, we're just kind of taking a systematic assessment of periodic trends, things like electronegativity, polarizability, right? We're taking a look at this aldehyde or ketone, and we're saying that carbon that's double bound to the oxygen, it has 2 bonds pulling away electron density towards an electronegative atom. Even though that oxygen has lone pairs on it, because it's bound to our carbonyl carbon versus the oxygen with 2 lone pairs, that's our alcohol, we can go ahead and see that's less sterically hindered, and we can go ahead and identify that as our nucleophile. Then we took some sort of acid, and we went over a couple of them that I'll review. And at the end of the day, if we have a aldehyde, if one of these R groups is going to be H, then we get a acetal. So we go from an aldehyde, if that's what we started with, we get an acetal. If we started with a ketone, then we get a ketal. You'll also recall that we lost water in this reaction, right? We identified in the mechanism, it's really important for us to understand how we're going to lose water. And the oxygen here in water is coming from our ketone or our aldehyde, right? We have a couple of candidates for this water oxygen to come from. Could have been from our nucleophile. We see oxygen there, but we can go ahead and identify the fact that that water is going to come from our ketone or our aldehyde. And we can take a look at that through a mechanistic lens. So we said this reaction is under equilibrium, and so we could said that we could drive our reaction forward in the same sort of Le Chatelier's principles, right? So we can think about Le Chatelier's principles, right? So if we remove a component from our products, such as water, we can go ahead and drive our reaction forward. If we add more of one of our starting materials, our electrophile or a nucleophile, we can also drive equilibrium forward. So we learned a lot of these tips and tricks from Fischer esterification reactions when we talked about them. And this is how we get it to go towards our product, as opposed to being stuck in this equilibrium here. We also talked about on Wednesday that our acid catalyst can help to aid in pushing our equilibrium forward, or it can actually harm it. All right. So if we use H2SO4, which we can, it's a strong enough acid for this. That's an aqueous acid. So we have water there, meaning we're kind of driving our equilibrium towards our starting materials because we have water as one of our products. So you can use things like HCl, which it can oftentimes be in water, but we can also form this non-aqueously. And then we also learn this new acid, tosic acid, which we abbreviated TSOH. Right, and tosic acid is actually an abbreviation in and of itself. In terms of para-toluenyl sulfonic acid. So let me draw out that complicated name for you. All right. And if we look at this half of the molecule, this looks a lot like sulfuric acid, right? So it's a very nice, favorable pKa. We can use a catalytic amount of it. And it doesn't have water associated with it like H2SO4 does. And so when we're thinking about driving the equilibrium forward, we often use tosic acid for this. The other reason practically in the lab why we use this is it's a solid. You can weigh it out on a bench top, as opposed to sulfuric acid, which is, a liquid and highly corrosive. So all right, so this mechanism started off very, very similar to things that we've seen in this chapter already, but then we did something that I want to review that's a little bit different than what we've seen, and it contrasts to things like maybe our intuitive SN2 mechanisms and things like that. So we're going to go ahead and review that fourth P. All right. So P4 for this reaction, I'll use acetone as our ketone as an example, different than what we had last time, which was an aldehyde. And let's use tosic acid in this case. All right, so we will use tosic acid. And we'll add in our alcohol in just a moment. But first here, we're considering in this reaction that we have, if we take a look at the structure of tosic acid, something that looks pretty acidic, right? We have all these electron withdrawing groups ready for that H to be deprotonated. And so we can go ahead and take the lone pair of electrons on our oxygen. We can attack that H, break that OH bond, and give that back to our tosylate, which would be our counterion. And what that's done for us is this has made our electrophile a stronger electrophile because we now have it protonated with that positive charge. We'll carry through our tosylate counterion as well. All right. Just to balance our charges, and I'll come back in a moment. Okay, now that we have our stronger electrophile, now we're ready for it to react with a relatively weak nucleophile. All right, so we can think about our alcohol. Let's use tert-butanol as our alcohol here. We have a couple of lone pairs of electrons on our oxygen. That's going to behave as our nucleophile. We take that electron density from the lone pair, we add it and have it attack that carbonyl carbon. Then that means we need to break our CO double bond. Otherwise, we would have 5 bonds to carbon, which it can't accommodate. So we break that CO double bond and return those electrons to our oxygen. All right, that's going to get us to a tetrahedral intermediate. So now we've quenched the positive charge on our carbonyl oxygen at that 1 position. And we have added in our tert-butanol, which means that it has a positive charge, right? We haven't done anything with that proton in the alcohol yet. We'll carry over our tosylate counterion to balance all of our charges. So now we can think about neutralizing this species, all right? We can deprotonate that acidic OH bond, return the electrons back to our oxygen there. And then what we get from that reaction is we have regenerated our acid catalyst. And we now have an alcohol. And I'm just going to do a quick bond rearrangement so that we can see this more easily. We have our tert-butanol. And let's draw in our tosic acid to recall that we've reformed it. So truly means this is a catalyst. We haven't used this up anywhere. We've gone ahead and regenerated this catalyst. All right. So now we have a couple of options. At the end of the day, we take a look at our product that we formed from this reaction and we say, well, we need to lose an equivalent of water and we also need to add in another equivalent of tert-butanol. So how are we going to do that? Well, we're going to go ahead and make this alcohol in our molecule into a good leaving group, right? So under acidic conditions, we wouldn't want an OH leaving group, but would be perfectly fine with a water leaving group. So we're going to go ahead and deprotonate that tosic acid, return those electrons from the OH bond to our oxygen. And now what we have is, you'll recall this was called a hemi-ketal intermediate. It would have been a hemi-acetal intermediate if we had had a aldehyde, but we have a ketone starting material, so it's a hemi-ketal. So hemi is sort of like halfway, like hemisphere, right? That's half of the earth, so a hemi-ketal is half of a ketal as our intermediate to get to our ketal. All right, let's draw the product of those arrows that we just drew. So now we have a protonated species. We have this hydrogen that's now been added to our alcohol, meaning that alcohol is now protonated and positively charged. We really have not done anything with our other equivalent of tert-butanol on the other side. Now, I often get the question, well, why didn't you protonate the ether, the oxygen of the tert-butanol? Well, this is all in equilibrium. That would absolutely positively happen. It wouldn't lead to productive reaction. So it would go back, it would sit there for a bit, and then equilibrium would carry it back into a more reactive intermediate. So I often get that question. It's like, why didn't we go down this different pathway? Well, whenever I'm showing you a mechanism, I'm showing you the productive way and the productive pathway to product. But knowing there's a lot of other things going on, especially when we have equilibrium arrows and things like acid catalysts, all right? So I'm always going to show you the way towards product. But if you're doing a mechanism and you ever get caught up and you do the wrong thing, just go backwards until the steps get back to the point where it makes sense. Okay, so now we have this opportunity. Let me draw in our tosylate counterion. We don't need it quite yet, but let's just make sure we have it and carry it forward in our reaction. Okay, so this was the step that I was wanting everyone to really think a lot about in terms of how this reaction works. So I have a lot of people that want to take, so don't draw this in pen. I'm going to erase it in just a moment, okay? But I want to illustrate what a lot of people want to do. So a lot of people want to take tert-butanol lone pairs and attack and have the water leave, right? This is what a lot of people want to do, an SN2 reaction. But what we'll see here is this is a very, very, very sterically hindered carbon center. So we're not going to go ahead and do that. Instead, what we have is the opportunity to do an intramolecular reaction, right? We can assist water leaving by using a lone pair of electrons on our oxygen that go and come down and make a CO double bond. And that's going to cause our water to leave, giving its lone pair of electrons back to it. All right, so we can take a look at what we have here. What we have here is now that taking that lone pair of electrons from our tert-butanol piece of our ether, what we have is a positively charged oxygen, and we have tert-butanol. Or tert-butyl group bound to it. All right, we've lost water. We've accomplished what we set out to do, is we've lost water with 2 hydrogens from our alcohol and 1 oxygen from our ketone in this case. And then, of course, we always have our tosic acid as our counterion, and we just need to keep track of that. Need to regenerate it at the end of the day, right? All right, so now what you'll recognize is mechanisms are not about memorizing every single arrow. They're about understanding fundamental principles. It's like solving a puzzle. What comes next based on reactivity, right? When we solve a puzzle, we're trying to figure out like a puzzle, like an actual puzzle. You're trying to figure out what fits where. Well, we're trying to figure out what is the next logical step in this mechanism. So what we'll notice is that this compound right here, this protonated ketone intermediate that we then had our nucleophile attack, looks remarkably similar to this alkylated intermediate. That oxygen is positively charged, increasing the electrophilicity of this. And so these look remarkably similar. And so we can recognize the pattern and say, I bet you they're going to react remarkably similar. So this is where we reintroduce our other equivalent, right? In our reaction up here, we said we had 2 equivalents of our nucleophile. Here's where the second one comes in. And just like we saw before, our tert-butanol is going to go ahead and attack this electrophilic 2 position of our carbonyl carbon. We're going to break that CO double bond. We're going to break that double bond, turn it into a single bond, and return that lone pair of electrons back to our carbonyl carbon. All right, so we're getting close to what we want our product to look like. We now have all the correct bonds made to our carbon, right? We have this O tert-butanol. I don't like how to draw that. We have our O tert-butanol here. We still have our oxygen bound to both tert-butyl on the bottom as well as a proton, meaning that we have a hydrogen there. And then we have our tosylate counterion that we've been carrying throughout. So now we have all of our bonds being made, and now we can bring this home and we can just do a proton transfer. We can regenerate our catalyst by deprotonating that OH bond, returning that electron density from the bond. Those 2 electrons now return to oxygen to be able to give it a lone pair. And at the end of the day, we get out exactly what we were hoping for from this mechanism. So we have our oxygen from both of our alcohols. You can do a bond rotation if you want to make it look like you want, but here we go at the end of the day. So recall, this was kind of the step that we hadn't talked about before. The rest of it is a lot of pattern recognition, but we're actually going to see this lone pair assisted leaving group situation over and over and over again. It doesn't even have to be water. It can be other types of good leaving groups. This key intermediate after a hemiketal is really going to show up a lot. So that's why I wanted to make sure that everyone got a chance to kind of go through this slowly with me in class. All right, so now I promise some what I think is exciting chemistry, which is the idea and the concepts of using groups to protect other groups. Yes, question. Yeah, that's a great question. So the question is, for those who couldn't hear, what about stereochemical considerations? So I think that's a really great question. So if we take a look here, in this particular example, because we have matching alcohols, we can't add two different ones. We're always going to have the same group here, so it will never be a chiral molecule. So that's a really great question. So no worries about stereochemistry in this particular reaction, because both of those are the same group. Even if R1 and R2 were different, it wouldn't matter because those are the same group. So it'd be the same molecule. So great question. All right, so now our protecting group ideas. And so this is learning objective 18J, which is the 2 Ps. It turns out you already know the 4 Ps because it's this exact same mechanism here, just with a diol instead of 2 equivalents of alcohol. But we're only going to test you on the 2 Ps of cyclic ketals and acetals for protecting groups. Keep saying this phrase, protecting groups. This is in 18.9. Well, they're exactly what they say. They protect functional groups from being reacted with. So overall, what we're going to do in this reaction is we're going to take some sort of aldehyde or ketone. This is going to be our electrophile. We're going to take a diol. Okay, and this is going to be our nucleophile. We want to make sure that this is going to go fully to completion. So we're going to remove water with a Dean-Stark trap. Remember, I introduced that for Fischer esterification reactions, and it pulls water out of the reaction. So we'll just note that this removes water. It's actually a physical piece of lab glassware that allows for distillation and removal of water. The very first reaction that I set up as an undergraduate involved a Dean-Stark trap. And what we get out at the end of the day, before I was drawing R's on these oxygens because they were 2 equivalents of an alcohol. Well, now we have a diol, so they just remain connected to each other. Okay? So we call this a cyclic acetal or ketal. So some things to note, all right? This carbon length, this linker here, this can be any number of carbons. Reasonably speaking, we usually see 2, 3, or 4, because otherwise you form a really large ring. And you'll remember from 2301, very large ring systems are not very favorable, but technically speaking, it does not have to be, this is ethylene glycol, which is like in your car for antifreeze. It does not have to be ethylene glycol. It could be any number of carbons. All right, so the definition of our protecting group is we use cyclic ketals and acetals to protect carbonyl groups. So these are aldehydes and ketones. So we protect carbonyl groups from further reaction. Or we are protecting the diol. From further reaction. All right, so let's talk through some scenarios. Now that we have our technical definition, say one of our R groups here was an alkene, right? And we wanted to hydrogenate our alkene. And we wanted our final product to continue to have a ketone. Now, we know you can hydrogenate alkenes with H2 and a metal catalyst like palladium. So if we tossed in H2 and a metal catalyst, and this was our alkene here, it would go away, but also we would turn this into an alcohol. That's not what we want. So what we would do is we would put a protecting group on this. We would turn it into a cyclic ketal or acetal. Then we would add H2 and palladium, and it would not react with our acetal or our ketal. All right. Say we wanted to add a Grignard reagent to this, right? That would react. We often use protecting groups. Say we had two, we had an aldehyde and a ketone in our molecule, and we only want our organomagnesium reagent to react with one of them, then we protect the other one, all right? We also might have a complicated molecule up here that we really want to react with. Say we have a benzene ring with this diol on it, and we want to react with a organometallic reagent, all right? We have an aerobromide. We want to make an organometallic reagent out of it. That would just deprotonate this OH of our diol. So we would protect it so that OH is protected. And then at the end of the day, we would do something called deprotect, all right? So let's take a look at how we get off our cyclic ketal or acetal. So this is that's the protection reagents. And now say we have our cyclic ketal and acetal here, and we want to get our ketone back. Well, we're going to use a little bit of water. We're going to use acid, and we're going to use heat. All right, so you just mix this up with a little acid, you add water, and then you get back your ketone or aldehyde. All right, well, why is that? That's kind of crazy. We added acid to make this. Why are we adding acid to get rid of it? Well, this is why we reviewed our mechanism, all right? So whenever we have equilibrium, we can always go backwards, okay? So instead of this sequence going forward, if we add a bunch of water, which we lost, we can add a bunch of water to our reaction and have it go in the opposite direction, get back exactly where we started. That's how equilibrium works, right? So that's why deprotection conditions look eerily similar to our protection conditions, except for here we're removing water because we want to go in the forward direction. Here we are taking out, adding in water because we want to go in the reverse direction. Yeah, question. So I wanted to indicate where we get each of our components from. So I just drew it in a different color so that you can see that it came from the water. So there are the same ones. Oh, I see. You're talking about, I just did a bond rotation. Yeah, we can absolutely not do a bond rotation. It would do the same thing. Yeah, question. Yeah, that's a great question. This is something chemists think about all the time. It's kind of the fun of it, of the different puzzle pieces. So what we would do in that case is this is where our equilibrium and KEQ that we learned last time related to electronics and sterics come into play. So we might look at our ketone and our aldehyde. If we wanted to protect our aldehyde, we would make sure we had a bulky protecting group so that it would just react with the aldehyde. Or we could take a look at our electronics, and we can selectively add things to the identity of our nucleophile to favor the electronics of our aldehyde or ketone. So yeah, that's a great question. Like, it's called chemoselectivity. And this is why I love chemistry, is like putting all these little pieces together because there's so many other considerations. So yeah, great question. All right, so let's go ahead and do some chime-in questions. All right, let's kind of get some of our conditions down here. And I think I finally figured out how to get chime-in to actually work on my iPad. So yeah, let's kind of take a look. I told you we can use a lot of different alcohols. It doesn't have to be that diol, that's ethylene glycol. What do we think about these starting materials? What would work here to make this particular protected cyclic ketal? And leave your chime-ins open because we'll do one afterwards where we're doing the same considerations. All right, what starting materials? How can we make this? All right, wait for, as always, you're welcome to check with the person next to you, see if you got the same answer, and debate it out if you didn't. Right. It's a little bit challenging to see, so let's go ahead and start to see where people are at. Okay, so let's take a look at what people are thinking. Okay, so we have a lot of answers for B, which is great. So what we did here is in B, we counted the number of carbons attached to our oxygens, and we said that there's a 3-carbon linker, and that's what B represents. A would have also given a cyclic ketal, but it would be the wrong number of carbons for that protecting group. These other answers with our Grignard reagents would give us some alcohols left over, but it wouldn't protect our ketal. So I really like that people are recognizing that carbon linker length is really important. All right, let's check in on our next question. I'll leave that open for a little while longer. Okay, so now what about this? Maybe instead of going backwards, we're going forwards. So instead of predicting our starting materials, what is our product of this reaction? All right. So we have a couple of different options here. So let's see what people are thinking. Oops. Okay, view results. All right, so we have some confusion between A and B, and I think that's probably the two that I would think would be the most confusing. So let's take a look at A and B. So A, we have 2 carbons from our, 3 carbons in our linker here. So we can see that gives us a 3-carbon linker, but so does B. All right, and what A is showing that our acetone has 3 carbons. And remember, we lose our oxygen from our ketone. And so we go ahead and lose that oxygen from our ketone. So in this case, acetone, we're looking for 3 carbons, and that's what gets us to A. B would be having 2 equivalents of acetone incorporated, but we see here oxygen in this case has 3 bonds to it, so it would be positively charged. But I definitely see why people see that answer, because it's easy to identify where the acetone is. But in this case, we would be getting answer A. So, all right, great. Looks like people have responded. Again, if you have chime-in issues, then let me know after class. All right, so let's go ahead and do a couple more examples here of those functional groups that I was talking to you about that we can think about protecting. So this is learning objective 18L. This is to actually use protecting groups in multi-step synthesis. All right, this is that last question on the exams and the midterms and the final is always multi-step synthesis. We're always thinking, how can we put things together? Because that, as chemists, is what we love. We love thinking logically. That's what chemistry is. Okay, so let's go ahead and say that this was our starting material. We have these fun little ambiguous multi-step arrows that we have. And at the end of the day, we're going to get out this particular product. All right. So whenever I'm doing multi-step synthesis, I'm always thinking, what things are we adding? What things are we taking away? Okay. So we are adding in let's count our chain, 1, 2, 3. 1, 2, 3. We're adding in a 4th carbon. Okay. So we're adding in a 4th carbon, and let's go ahead and say that we need to break between carbon 3 and 4. Okay. Seems reasonable. Let's take a look at if we broke that apart, what our retrosynthesis would look like. 1, 2, 3 carbons. 1, 2, 3. And we can think about this fragment here as our other fragment that we need. That's where our bond is breaking apart for our 4th carbon, okay? So now whenever we're thinking retrosynthetically, we're thinking like, what's our nucleophile? What's our electrophile? Well, we know we can make alcohols from organomagnesium reagents, organometallics, and aldehydes. So if we turn this into an aldehyde, like benzaldehyde, it looks like a great candidate for us to be able to add a Grignard reagent or other organometallic reagent, right? We see that this is our nucleophilic portion. We see that this is going to act as our electrophilic portion. We can put them together. Okay, this seems like a great idea, right? We know how to make alcohols, and this seems really easy, but we can identify we have an issue here. We cannot have a Grignard reagent in our reaction. We want it to react with this aldehyde, but we're going to tell it can't react with this aldehyde and another equivalent of the starting material, or it can't do a cyclization reaction. We can't do that, and that's where protecting groups come in, all right? So now we can identify that this spot here needs a protecting group. Right? We know that organometallic reagents will react with aldehydes, so we cannot have this in our reaction. All right, so this is the logic. This is the puzzle pieces that we're sort of trying to put together, the mystery we're trying to solve. Okay, so now let's go in the forward direction. So this is what we're looking for in an exam, is how do we get there? What are our reagents and our starting materials? So I'll just copy down this. I'll copy down our product. So 1, 2, 3, 1, 2, 3, 4 for alcohol and our phenyl group. Okay, so I would say let's go ahead and protect this. Let's go ahead and add in, we can use whichever diol we want, but let's use this 2-carbon linker one. Pretty easy. Let's add in our tosic acid and our Dean-Stark trap. Right? If we do that, we're going to go ahead and we're going to protect our aldehyde from reacting. We haven't done anything to our 1, 2, 3 carbon fragment or our bromide. All we've done is we've just protected our aldehyde from reacting. All right, great. Now we don't need to worry about things. We know that we can add in magnesium, and we can go ahead and we can make our Grignard reagents. All right, we could have added in lithium if you wanted to make an organolithium. That's fine too. So now we make this magnesium bromide. Our acetal and ketal is still protected. Awesome. Now we can go ahead and react this with the other carbon that we want to add to our chain and our phenyl group to make this into the product that we're looking for. All right, so we would add all of these things together. And then I have not left myself very much room. I'm going to move this up. Okay, so now we react these things together. We keep our acetal protected. Nothing's happened there yet. Notice I did not add a second step yet for our quenching of our organomagnesium reagent. Added in our carbon, we have an alkoxide. That's our magnesium bromide alkoxide here. And guess what? We know our deprotection conditions involve acid and a little bit of heat and water. We also know we have to quench organomagnesium reagent reactions with a little bit of acid and water. So we actually get a 2-for-1 special just by adding in some H3O plus, warming this up a little bit, and then we get to our product. Now on an exam, if you were to not remember those are the exact same conditions or you needed to add a little bit of heat, you could do them stepwise. That's totally fine with me. You could quench your organomagnesium reagent with H3O+. You could get your alcohol there. And then if you wanted to add in tosic acid, doesn't matter. I'm just looking for, there's so many right ways to do chemistry. Yes, there's wrong ways, but if you have a creative way to do it and it takes you one extra step, that's no problem at all. All right. So this is how we get there. Okay, let's do another practice problem. All right. So these are the ideas that we need to be thinking about. Let's identify other functional groups we could potentially want to protect. Okay, so here we have a ketone and a carboxylic acid on this molecule. Right? And we want to turn this into an alcohol from our carboxylic acid. We basically removed this oxygen at this position. No adding carbons, nothing. We just removed oxygen. Right? We know removing oxygen or bonds to oxygen is a reduction, right? We know that. So the only thing we know is lithium aluminum hydride followed by a water quench. We know this takes carboxylic acids turns them into alcohols by reduction. All right, awesome. So we know there's only one reaction that turns carboxylic acids that we know of. There's many exist in the world, but from the textbook, there's only one we know. But what is our problem here? Well, the other thing that happens is we turn ketones can get reduced as well. So if we add lithium aluminum hydride, we're not going to selectively reduce that carboxylic acid down to an alcohol. Instead, we're going to reduce our ketone as well. So this is another perfect scenario for a protection. All right. So we need to protect our ketone. Right? Because that reagent would destroy it and we would not get to the product that we wanted. All right, so let's go from what we think we can do here. So let's go ahead and immediately protect that ketone. All right. We'll add in whatever we want. We can add in, I always like ethylene glycol, it's just easy. But you could use another carbon chain linker with your alcohol. Let's add in tosic acid. We'll do this in the lab with the Dean Stark trap to remove our water, drive this to completion as a reaction. We've protected our ketone. Recall, even though we have a carboxylic acid, we did not learn that cyclic ketals and acetals react with carboxylic acids. They don't. Even though we have a carbonyl carbon, a carboxylic acid functional group is different than a ketone functional group. Sometimes they react the same, like with the lithium aluminum hydride, and sometimes they react different. So in this case, because they react differently, we can protect that. Now we could go ahead and add in our lithium aluminum hydride, add in our water. We would have reduced down our carboxylic acid. It's getting closer to exactly what we want it to be, right? We've reduced that down, so we've accomplished our goal of removing that oxygen through a reduction. Now we can just add in a little bit of H3O plus and heat, and we get to our product, right? We can do the deprotection. So this is what we have to do. We have to protect something so we don't destroy it. We do another reaction with a reagent that it would be incompatible with, and then we deprotect it. All right. So let's do one final example in our class today, and then it is spring break for you all and for me. All right, now let's say we want a diol. Before our previous examples, we're dealing with carbonyl groups, but I also said we can protect diols, right? So say we wanted a multi-step synthesis. At the end of the day, we want to keep our diol, but we want to add a carbon and an oxygen to it. So let's go ahead and number our carbons, 1, 2, 3. 1, 2, 3, and now we identify we've added a fourth carbon, right, in the place of that chlorine. So how are we going to do this, right? I think a great way would be through an organometallic reagent. We can make an organometallic reagent here, and then we could add it to formaldehyde, and that would give us a carbon and another oxygen. It would add in carbon number 4 and our third oxygen. But we cannot make that into an organometallic reagent with those free alcohols, because we know organometallic reagents go ahead and they react with organometallic reagents. So instead of doing the desired reaction, you would just deprotonate your alcohol. All right, let's go ahead and protect this, all right? In this case, because we already have our diol in a reaction, we're gonna use a carbonyl group, and in this case, acetone, to do our protection of our reagent. So we would add in our tarsic acid and our Dean-Stark trap. We would tie up those alcohols. We can still have our chloride here, all right? So this fragment here, this is from our acetone. All right. So previously we had focused on adding in a diol to protect a ketone. Here we're adding in a ketone to protect a diol. Then we can go ahead with our lithium reagents. We can add in our 2 equivalents of lithium. We still have our protected diol. Now we have our lithium here. We can go ahead and add in our formaldehyde to add that third carbon, or sorry, our fourth carbon, carbon number 4. And then we can just go ahead and do our deprotection conditions with H3O plus and heat. And we end up with our product. Right, so previously we protected a ketone with a diol. Here we're protecting a diol with a ketone. You can do either one, because at the end of the day, it depends on what you want at the end. All right, we'll do more examples. We'll see a lot of functional group tolerance in the rest of this class, but that is what I will leave you with. Everyone has a good and safe spring break.